This is Jack Jackson. Now we're going to learn an inverse function rule for finding the derivative of an inverse of a function which we know the derivative of. So we know the derivative of one function, and we want to use that to help us find the derivative of its inverse function. So if f is the function we know the derivative, how to find the derivative of, we can take the derivative of f inverse x, and it turns out to be 1 over f prime, but evaluated at f inverse of x. And so the way we're going to prove that is we're going to make use of what it means to be an inverse function, and then we're also going to make use of the chain rule. So here's how it works here. You let y be f inverse of x, and so what we're looking for then is dy over dx, the derivative of y with respect to x. But if y equals f inverse of x, that means x equals f of y. That's the definition of what an inverse function is, basically. So now we just take the derivative of both sides with respect to x. Now the easy side is the right side. Let's do it first. The derivative with respect to x of x is 1. Now the derivative of f of y is f prime of y. That's df over dy. But then it's times dy over dx, because y is a function of x. We're applying the chain rule on the left. Now we want to solve for dy over dx, so we divide by the f prime of y, and we get dy over dx is 1 over f prime of y. But what is y? Y is f inverse of x, so dy over dx is 1 over f prime, evaluated at f inverse. Now we can use this to find the derivative of anything that we know how to find the derivative of its inverse. So we're going to use that particularly to find logarithms, to find a derivative for a logarithmic function. Okay, so here we go. So if f inverse of x is ln of x, then f of x is e to the x. So those are inverse functions. So the derivative of ln of x then is 1 over the derivative with respect to u of e to the u, but you evaluate it where u is ln of x. Of course, the derivative of e to the u is e to the u, but in the place of the u, we want to put in ln of x. So it's 1 over e to the ln of x power. But remember that when the base of the logarithm and the base here of the exponential are the same, which they are here, they undo each other. They're inverse functions, so they cancel out. And so you just get 1 over x for the answer. Now, we can do the same thing without using the shortcut rule, but we're just using the same steps that we used in the derivation of that inverse function rule. So I'll do it out that way as well. You'll see it's the same thing is happening. So you let y be ln of x. Come back. Okay. Y equals ln of x. So that means that e to the y equals x. Take the derivative of both sides with respect to x. On the right, like before, we got a 1. Derivative of x is 1. The derivative of e to the y, we've done a substitution now, or a chain rule, where y is a function of x, so that's e to the y. The derivative of that is e to the y times dy over dx. Notice the application of the chain rule. Now we divide both sides by e to the y, and so we get dy over dx is 1 over e to the y, but y is ln of x, and e to the ln of x again is x. So dy over dx is 1 over x. The derivative of natural log of x is 1 over x. It's kind of an amazing thing if you think about it, because the logarithm is this not just a basic function out of algebra like out of not a lot of polynomial type operations, but we get a nice rational function out of that for a derivative. Now let's see if this makes sense. Now first of all, we need to put a restriction on here. So because 1 over x is actually defined for all real numbers except for 0, but ln of x is only defined for positives. So we need to put that restriction for this to be true. So we need to have the d over dx, the derivative of ln of x is 1 over x for only x positives. So let's take a look at the graph and see if this makes sense on the graph. Okay, so ln of x is the blue graph. It's only defined when x is positive. Notice it's increasing everywhere, so the derivative, 1 over x, which is the red one, is always positive. Makes sense. The original function f of x is concave down, so its derivative is a decreasing function, which we see here. The original function has a vertical asymptote at the y-axis, and so does the derivative. Makes sense? As we go further out to the right, this one is getting more and more towards being flat, so the derivative is getting more and more towards being 0, and so we have an asymptote there on the derivative. Looks just right. It has the properties we want to do. Now, I want to show you something else we can do. Consider this if you did ln of minus x. Well, this is only defined when minus x is positive, which means x is negative. So this one's only defined when x is negative. Now, what would that give us? Well, according to the chain rule, this is derivative of ln of u, so it's the derivative of ln. It's derivative of ln of u. It's 1 over u being minus x, times the derivative of the u. Derivative of minus x is negative 1. The negatives cancel, and you get 1 over x. Oh, that's interesting. So if x is negative, the derivative of minus x is also 1 over x. Okay, now wait a minute. Let's think about this a minute. Remember that the absolute value of x is x if x is greater than or equal to 0. It's the opposite of x if x is less than 0. So if we do the derivative of log of absolute value of x, when x is positive, this is the derivative of log x, which is 1 over x. When x is negative, this is the derivative of minus x, and the derivative of that's also 1 over x. So d over dx of ln absolute value of x equals 1 over x, and both of these functions are defined, both the original and the derivative are defined for all real numbers except for 0. So this condition, it's kind of optional if I write it because it's still implied by this over here. Now let's take a look at the graph again and see if this, once again, is going to make sense to us. Well, let's see, what do we have here? The original function's in blue. So log of the absolute value of x is just the log of x for the positive x's up right here. And it's the log of the opposite of x for the other one, so it's just a reflection over the y-axis. And notice the blue one's now defined for all real numbers except for 0. When x is 0, we have a vertical asymptote there, and so the derivative has a vertical asymptote. We already talked about the characteristics of, it's the same graph here in blue that we have for just ln of x for the increasing part over here when x is positive, and we already noticed that 1 over x is the right shape of the graph there. Let's look over here for when x is negative. The original function is decreasing, so its derivative is negative. So it's down in this third quadrant, which we see that it is. Furthermore, as we go further and further right, we're getting closer and closer to horizontal. So that means its slope's getting closer and closer to 0, and so we have a horizontal asymptote of 0 on the left. Again, we have a vertical asymptote here at x equals 0, and so that's going to be true on the original function, so that's going to be also a vertical asymptote on the derivative. Finally, the original function over here when x is negative is decreasing, so that means the derivative is negative. It's also concave down over here. So concave down for this part means the derivative will be decreasing, which you can see that it is. Whereas over here it's also concave down, so you see the derivative decreasing on that piece as well. So yeah, it seems to work just fine. Now, before we go any further, it might be useful to remember a few things about logarithms. Remember that logarithms, the word logarithm is completely synonymous with the word power or exponent. So, if I have y equals b to x equals b to the y, I could call that y the power, the exponent, or I could call it the logarithm. So when we say y is equal to the logarithm there, we're just saying y is the power in this version over here. So when I write x equals b to the y, that is a relation of set of ordered pairs x, y that make that true, or b some constant. The same set of ordered pairs are on this one, y equals log base b of x. It's the same equation, one solved for x, one solved for y, just like if I have y equals x plus 2 is solved for y, or I could say x equals y minus 2, that's the same equation solved for x. So I can solve it for x or for y, and it's equivalent. So f of x equals b to the x, and f inverse of x is log base b of x, are inverse functions. And so that means if I do one and then the other, they cancel each other out. So if I first do log base b of x and then do b to that power, they cancel each other out, leaving only the x. Or if I do it in the other order, do b to the x first, then do log base b of that, again they cancel out, giving x. That's that basic property that if you compose f with f inverse, you get just the input that you started with, x. Okay, what other properties do we have of logarithms? Well, the log of a product is the sum of the two logs. So log of x times y is log of x plus log of y, all with the same base b. This is equivalent to saying the logarithm on the product is the sum of the two logarithms, or rephrasing, the exponent on a product is the sum of the two original exponents. And that's really just the pattern, that's really just the property x to the n times x to the m is x to the n plus m. And when you prove that, that's really all you're using in the definition of logarithms. Similarly, the log of a quotient is the difference of the two logarithms. That is, the exponent on a quotient is the difference of the two exponents. This is exactly saying the same thing as b to the n divided by b to the m is b to the n minus m power. So that's one of our power properties, exponent properties, and here it is written out in logarithm form. So we can kind of combine these rules and write it this way, and by this I actually mean something more general than what I've written down. Log base b of wx over yz, every one of these factors gets its own logarithm if we want to expand it out, and it's base b for all the logarithms. The ones that are in the numerator have coefficients of positive 1 in front, and the ones that are in the denominator have coefficients of negative 1. Or, put it the other way around, when can you combine these all into one logarithm? When they're all the same base, and they're all coefficients of either 1 or negative 1, they can be redone this way with the things inside the logarithms on the right becoming things that are multiplied on the left, with the ones with positive coefficients going to the top and the ones with negative going to the bottom. And it doesn't have to be 2 in the top and 2 in the bottom. There can be any number of factors in the top, any number of factors in the bottom, and this works the same way. Now we also have a property of powers that says x to the n and raise that to the m power is x to the n times m. Well, when you have a logarithm of a power to a power, then you're multiplying the powers. Well, basically the one power is n and the other power is the logarithm. And so basically it says we have log base b of x to the n, it's n times log base b of x. At least if n is an odd number, this works out. If n is an even number, then to make the domain issues work out, then you need absolute value here on the x. And ln of x is just another way of saying log base e of x. And usually if you see log of x without a base or an invisible base, they mean base 10. Although I have seen some books and computer languages that when they say this, they mean base e logs. But usually this is base 10. These are called common logs. I kind of put common in quotes these days because they used to be commonly used for lots of calculations. Now we use calculators to do those same calculations. So they're not so commonly used anymore. They are used some though. Log base b of x can be written as log base a of x over log base a of b, so you can switch from base b to any other base. In particular, the base we want to switch to is our standard base of e. So log base b of x is ln of x over ln of a. Notice the we have that. What is ln of? That's not supposed to be there. That's supposed to say ln of b. Fix that typo. So we can basically change from any base to any other one. The b is already kind of low as a subscript. That's the ln of b that goes in the bottom. Sometimes you'll see e to the x written as exp of x, particularly in some computer programming this is one way you'll see e to the x done. And of course, e is defined to be the limit as, well, one way you can write it is this. We actually defined it this way. I'm going to write it a different way, the way we defined it in our class. We did ours as n goes to infinity. This power was what was up here, and the n was actually in here. And then we took the limit as n goes to 0. That's the form we defined it in this class. The other way I had it was actually an equivalent thing. And this is some of the digits that you get out of your calculator, and then e is an irrational number, so we could never list all the digits or even indicate them by some repeating or terminating pattern because it doesn't have it. So let's do a couple of examples where we apply this logarithm rule. Now I'm going to do this same problem two different ways, and it turns out we get the same answer. So the derivative of ln of 3x can be thought of as the derivative of ln of u, where u is 3x. So we've done a substitution. Then the derivative of ln of u is 1 over u times du, the derivative of the u. U is 3x, so that derivative is 3. 3's cancel here, and you get 1 over x. Well, that's kind of interesting. The derivative of log of 3 times x is the same as the derivative of just the log of x. Well, that's not so surprising when you think of it in terms of this next rule. Instead of starting with doing the derivative by substituting and doing the chain rule, we can use a property of logarithms first. ln of 3x is ln of 3 plus ln of x, which you notice is just a vertical shift of ln of x. Well, vertical shifts don't affect the derivative, because notice when we take the derivative of this ln of 3, since ln of 3 is a constant, that part is just 0, and then we have the derivative of ln of x, which is 1 over x. Okay, and then I'll let you work some more on these examples, and we'll come back with the next video and talk about the generalized power and exponential rule and a technique called logarithmic differentiation.